Okay, welcome everyone. Sorry about the 3-minute delay. OBS wanted to update, and then it couldn't connect to Twitch for some reason. I had to fix that. Very strange. Fixing it involved restarting the OBS, and it worked fine. I don't know. Also, sorry about the shirt. But you know, it's really hot in this room because I've got all these computers going, and I'm just not going to bother wearing the nice shirt today. Anyway, so I don't know why this thing is doing that. Okay, well now it's doing the thing where it, doesn't want to. It thinks black is a color, is chroma key green, and I don't know how to fix it. Let's see if I open the window. Hey, that helps a little bit. Okay, so technical issues. Sorry about that. Anyway, so today we're going to be talking about non-deterministic FSAs, finite state automata. Now, the issue is that I should switch to the class notes for that. So last time we talked about finite state automata, and we're going to go over the quiz. But today we're going to talk about, in order to understand P versus NP, which we won't get to probably. I might get to it shortly. I might get to it at the very end a little bit, but I'm not going to be able to do P versus NP the whole thing. So in order to talk about P versus NP, you have to understand what a non-deterministic Turing machine is, which means you have to understand what a non-deterministic thing is, because that's what the N in NP means, non-deterministic. So that's what we're going to do. That's actually the confusing part of the problem. I mean, problem's unsolved, right? So if you want $1 million, figure out if P and NP are the same thing. But there's $1 million bounty on that one. But if you can provide a proof one way or the other, we just don't know. And worse, according to Gödel's theorem, it may not even be decidable. So there may not be an answer. But if you could prove that, you'd also get the money. Anyway, so that's what we're going to be talking about today. Which is this thing that you have to understand, which is the non-deterministic part. But we don't have like 3 more classes left. This is our last class. Sad. This is our last class, so I'm just going to get to non-deterministic finite automata. And then if you're interested in P versus NP, and you may see it in your class, you'll have a leg up knowing, because now you understand what a non-deterministic machine is. So that's the plan. Are there any questions in chat? Okay. So, yeah. Sorry, I was 3 minutes late. So, this is today. Yes. And the TA is telling us all about the millennial problems and the prizes and the fact that one of them got turned down. So, okay. Very cool. Anyway, let's talk about the quiz. So our last little quiz, it's about finite state automata. And people have been telling me they're kind of fun. I think they're kind of fun too. This is why I wanted to do them. Because they're useful, heaven forbid, and they're kind of fun. That's the calculus notebook. Okay. So what state is the initial state? This is actually, it should be which states are initial states, because a machine can have, or no, I'm sorry, this is correct. Which state is the initial state? There's only one for a deterministic machine, and that's S1. How do I know that? It's got this little arrow there. It may have start. Some of them have start here written there. This one didn't. It's just got the little arrow there. So that's how I know where I begin. How do we feel about that, 1 to 5? Okay. Now, which state is the terminal state? Now, it's important to note that even a deterministic um, finite state automata can have more than one terminal state. Okay. But here the terminal state is indicated by that second circle. And it's that. It's also known as the accepting state. All of those things. All right, so how do we feel about that? The terminal state or the accepting state being designated by that double circle on it. Okay. Now, which state's the junk state? Well, the junk state is the place where everything lands, right? It's Hotel California right here. Right? It's only got it's got all of these ways to get in, and then you just loop inside, right? So we'll call that one Hotel California. You can check out anytime you like, but you can never leave. Ha. So that's S4. How do we feel about that 1 to 5? I know the book didn't go into junk states very well, and I kind of like breezed it a little bit. But how do we feel about that? Okay. The idea of the junk state here is that it accepts everything that doesn't have a valid entry, right? So here, if I had A, I'd go A here, but then I wouldn't go B. I'd go to anywhere else. And that lands into this junk state here. But it's not that it just accepts. It's that it loops itself for everything. So anytime I can't leave this state. It's not a terminal state. It's just where the junk winds up. Okay, it's a trap. All right, now if I feed ABA into this machine, where do I wind up? Well, here's A, B, A. I wind up at S2. How do we feel about that 1 to 5? Okay, there's a question in chat. Is it the equivalent of an error message in a program? It can be, but it's just it's the equivalent of a not match will never match thing. I mean, it's not just an error message. It's didn't match. An error message would be something like I could distinguish. I could say that the machine is only supposed to take A's and B's, and then have like an error message state where if you throw anything but an A or a B in, it goes no. And whether or not you call an error a valid accept is another question. I wouldn't, hence it's called an arrow. But the idea is that it's the thing where if you're not going to match, you just wind up there, and then I'm not going to spend any more computing resources dealing with it. I'm done with it. Okay. Now, AB, AB, AB. So if I go A, B, A, B, A, B, I wind up at a terminal state S1. So that's a yes. But the next one, AB, ABA, goes AB, AB, A. And I wind up at S2, and that's a no. Because S2 is not accepting. So how do we feel about the first part of question 5 there, 1 to 5? Yeah, so the question in chat is when it says accepted, that means a terminal state? Yes, or an accepting state. I don't remember. Which one does your book use? The literature. So I've got, when we started getting into this, I dug out the old Hopcroft and Ullman, which has different terminology than the book does. Oh, sorry, I just hit the microphone again. This microphone picks up everything, I swear. Regular expression, finite state automata, accepting. So your book uses the word accepting. The other book uses the word terminal, same thing. All right, the empty string. This one's tricky. I start here, and then where do I go? Well, nowhere, right? I start at S1, that's the initial state, and then I go nowhere. I end at S1. That means I accept, right? That's an accepting or a terminal state. Okay? So I'm going to accept the empty string. Right? I start here, and then I go nowhere. Well, that means I end on an accepting state. How do we feel about that, 1 to 5? This idea that the empty string starts at starts and goes nowhere. There's nothing to process. Okay. Now, if my finite automata had its accepting state, it did not have S1 as an accepting state, but had S2 as an accepting state, it would not accept, correct? Because it didn't go anywhere. Okay. Now the next one, A, C, A, B, A, C, I'm in the junk state. Okay, and the next one, B, A, B, B, A, B, A, A, B, B, A. Yes. How do we feel about those last two, 1 to 5? Okay. Okay. ACAB is like this. It goes A, C, A, B. Any other questions? Well, the second A follows this anything path, right? Because A is something. So the second A goes anything, anything, anything. You know, once I wind up in this state, anything comes back. So the question was the second A goes nowhere? Well, it does. It goes along the anything path because A is a thing, and it just goes back to junk. Yes. Are there any other questions? Okay. So let's look at this very quick. Let me see here. How could I open this up? A couple things. One, I made an announcement. Let me write some of this stuff down. And then my other announcement, blah, 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 and then at the end. Okay, so I want to go ahead and I want to talk about a couple of announcements. One, I made an announcement that said, if you're going to send me stuff, please don't use Canvas. Canvas is great. It's wonderful. But, you know, the problem is that I am literally on every calculus Canvas. Okay? So my inbox for my Canvas is absolutely useless, right? It's got 318 messages or 10 messages or whatever it is now, and I cleaned this thing out a few days ago. All right, it's absolutely useless. There are 1,000 calculus students sending me messages, literally 1,000 of them, and I can't possibly. I have a filter. I can't use the inbox on there. I have a. They go to my email. I have a filter to filter out your messages, but Canvas's forwarding thing is a little buggy. The other problem is that I can't forward, if you send me work, I can't forward that work to graders through Canvas. Okay, so you really need to send me, especially if you're sending me work. If you want to get in touch with me, especially if it's urgent, send me a Discord chat. If what you want to do is you've got old work that I've said you could submit or something like that, please send it to me via email, because then I can forward it to the grader and the appropriate grader for that assignment, because I have a list. Are there any questions about that? Okay. So that was the first announcement. The second announcement is, remember that the test is during class time on 4. Test 4 is during class time on Wednesday. Now, just like last time, there will be we're going to jump on Discord just like last time. We're going to use the phones. If there are issues, I'm going to have TAs with me. If there's an issue, we're going to deal with it then. Does anyone have any questions about that? And I put up, there was a question about the study guide. The study guide is posted. It's right here. I told you about the true-false thing. The test will be out of 110 points. People were asking, is it going to be mostly old stuff? Probably 60-40, 50-50. Test 3 was really 50-50 anyway. There's not as much material because there's only 2.5 weeks of class represented. And I used one of those to go over stuff that you missed, one of the quizzes to go over stuff that you missed on test 3. So, but today's lecture is on the test. So there will be questions about today's lecture on the test. Are there any other questions about that? Okay. So, yes, test 4 starts at 3:30 p.m. in class time. It is the last test. I am not allowed to have tests on Friday because of the fact that it's a reading day. So we have to do it on Wednesday, not on Friday. And we can't do it during exam week because we actually do have a final for this class that's optional. Okay. First thing we want to talk about, what proofs am I talking about? I'm talking about the I'm talking about the stuff that like this one, the halting problem. Um, right, I got this move to zero type thing. I can ask you one of those. If I run check halt on something like I did on the thing, the halting problem's a good proof that I can ask you questions from, true false ones. I wouldn't ask the Tower of Hanoi, but I might ask something like this. Um, uh, so read and try to understand this. I might give you some recursive function, and I did one. Um, this day was a write-off because you didn't like it. Um, oh, every positive integer is this is a good one. So so here we go. I have this check halt stuff. I have this question right here. The action like what is test? I could give you an easy true false one. Like this. Okay. I could give you something like this. Not that. Gödel's theorem's not good for this. I can give you something like this. Like I tell you that test A is while not check halt or something like that. I could ask you something like this. Uh, how you get the contradiction, that sort of thing. So reading and understanding these proofs is important. I could ask you about the idea about a machine taking its own code as algorithm, and I could compare that to a recursive function. Um, this, I like it, but, it doesn't work very well. This is good. The fact that I can induct and I find that there's a positive integer. Um, yeah. So those sorts of things are nice proofs. So those will be the proofy questions. They'll be true, false, multiple choice. I'm not trying to trip you up on them. Um, but and we are done with quizzes. Yes. So that's the kind of things that it'll look like. All right. Any other questions on that? All right. If you have more questions, I'm more than happy to do it. I will have extended office hours tomorrow, which I don't normally do, but I am going to have extended office hours tomorrow for you to ask questions. I'll be happy to jump on Discord, Twitch, whatever, to try to talk about some of these issues if you've got specific questions. Think it's going to be more like test 3 than anything else. Okay, it's going to be lots of multiple choice, some multiple select, some various some true false, some fill in the blank, but it's going to be very straightforward. Most of the questions are going to come for the quizzes. I might change some numbers. If they're not coming from the quizzes, I'm going to try to limit the number of points that the non-quiz questions come from. So if you're prepared for the quizzes, you're going to do fine. Are there any more questions about that? Okay, so let me start talking about stuff because people are going to ask me test questions all day, and I really do want to talk about non-deterministic FSAs, and I want to talk about complements. So today's objective is to talk about, okay, so objectives for today. The first one, and then the second one is define and give examples of non-deterministic FSA. I actually can't do that very well, can I? Let's do this. All right. Okay. There's a question about so there's a question about a machine taking its own code. Think of it more like a function's input is the letters f of x equals something. So the code itself, the function doesn't actually take itself as a function. That would be recursion. The idea of a function taking its own code as data is something like the letters. So the function takes the letters of itself as its input. It takes the sentence f of x equals x squared as its input. Okay. So what I want to do is define and give examples of, so define a complement. Okay, so I had this machine from the quiz, right? And it looked like this. It had a start. It had this kind of S1 state, which was just the accepting state. This was not an accepting state. This was S2. It was S3. And here was junk. And let's see, I think this was A, B. This one was B, A. This one was else, else, else. Oh. All right, does that look correct? Yeah. Okay. So now what I want to do is I want to define the complement of this. Now, what I want to do, this word, what would be a description of this machine, by the way? This machine takes, let's see, it takes start, the grouping AB, which is not to be, not the class, but the actual AB together, star, end. Does everyone agree with that? 1 to 5? How do we feel about that? That the connection between those two things? Okay. Um, so there's a question in chat. Does every regular expression need to be enclosed with that? In the book, no. The book is using generic regular expressions. I'm actually using um, I'm using regular expressions the way PHP uses regular expressions because I want the idea that this is code to stay together. That's a very good question. This end string, we're actually going to talk about ones that don't have start and finish positions. So this is the start position, and that's the finish position. That this is the start, and that $sign is the finish. But I'm going to get in today. One of the points of non-deterministic FSAs is getting rid of these things when I want to match anything in the middle. Okay? All right. This is called the language. Now, can I write a finite state automata that would accept anything but that? So how could I do that? Well, like this. Now, what I'm going to do is everywhere the initial states are the same, but I don't want to accept anything that this machine accepted. So that means getting rid of S1 as a as a um, as a terminal state. I don't want to accept anything that landed on S1. Is everyone on board with that? How do we feel about that? I want to ignore. How do we feel about that? 1 to 5. Okay. And then what I want to do is I want to accept every state that this thing would have rejected. So now I don't really have a junk state. Because now I'm going to accept all these states. Is everyone on board with that? This thing right here will accept, oops. This thing will accept C. Yes, it needed that line. This thing will accept C. This thing will accept anything as long as it's not accepted by the first state machine. Right? Yeah, so my junk state is no longer a junk state at all, is it? Now it's a terminal state. So's S2, so's S3, so's S1. I'm sorry, not S1. Everything but S1 is now terminal. Now, because every regular expression And I know I need to move it down. Because every regular expression corresponds to an FSA, the complement of a regular language is itself regular. And this is actually weird. Okay? This is not true for classes in general. Okay? This is something strange about regular languages. Okay. But, okay. So that's one thing. So you're going to see complement problems like this in other things. Like if you're talking about the complement of an NP problem, or the complement of a polynomial type problem, or the complement of a exponential problem. Okay, and a language is regular if it corresponds to a regular expression. Technically, it would be determined by a regular thing. Okay, how do we feel about that 1 to 5? That's a good question. This whole complement business. I've built a machine that rejects every word that the other machine accepts and accepts every word that the other machine rejects. And again, that's kind of a weird thing about regular expressions in these FSAs. They're very nice. Okay. All right. Now, we had a question about this orbit, and we had some other questions about these regular expressions. Okay. So let's go in. Let's talk about non-deterministic machines. And this goes into that, all of these various things. Okay. So let's look at one of the ones we had from last time. Remember, not that machine, not that one. Remember this machine here? This was a machine that accepted any word with a double A in it, right? This is called deterministic. Okay? Every output only has one way to leave a state. Okay? So this one no matter what it is, if this is A, if I'm at A, it's going here. And then it's going here, and then it comes back, right? And anything after A went back to the starting state. I can also draw that. Let's look at another machine that does the exact same thing. But this one's going to be non-deterministic. Now, what makes this machine non-deterministic is that A can go one of two places. And I actually don't even need this. Notice here I have two choices for A. Okay? I could have A being here and A being here. So let's trace the word here. Okay, here, if I want to trace the word, let's do this. And let me label some states here. So if I wanted to trace this input, what would happen? Okay, so here I would go S1 to S2 to S1 back to S2, then to S3, and then to S3. Okay, so does everyone see that? How do we feel about that trace, 1 to 5? So this is on the trace. This one was on the complement. Okay. Let's trace this one. So I started A. Now I've got two choices. I could go across A from S1 to S2, or I could stay at S1. I don't really have a junk state pointed, but that's the point. I wind up with junk. However, I could have also gone from S1 back to S1 along the anything. And then gone to S1 along with a B. Then gone to along the A to S2, then to S3, and then to S3 accept. How do you feel about that? 1 to 5. Oops, I missed it again. And the key here is that they accept the same thing. Yes, it's non-deterministic. Okay? Exactly. So, as long as there's a potential path to a terminal state, it's considered accepting. Now, this gets us back to the question we had about this OR business, and it also gets us back to these terminal initials. Okay? What if I instead of, let's look at the language. AA end. Okay? Now, if I don't have an initial, but I do have a terminal, right? If I don't have a thing, but I do have a terminal, how can I write this language? Well, this is the same as saying the following. Right? So, let's look at it. I know I want a state that's going to end, the thing has to end at A and A. So whatever it is, I'm going to have a terminal state here, and I'm going to have a state with A on it. Sorry. Now, here's my initial. And then I just have an anything here. And then I'm done. I don't need to deal with the issue of curving A's in the middle here, because I don't care. Right? I don't need if I wanted to do this with a deterministic FSA, right? If I wanted to do this with a deterministic machine, I would have to put here. So this is the in FSA here. If I wanted the deterministic finite state automata to do this, I'd have to do something similar, but I'd have to have one of these here, here, This would have to be, no, that's not an acceptor. This would have to be anything but A. This would have to be, right, this is A. This would have to have a state back here, anything but A. Here's an A. And then I've got this terminal state with all of these things here. Here's an A. So if I keep punching up more A's, I'm fine. But if I don't keep punching up more A's, I have to go back to the beginning. How do we feel about that, 1 to 5? I've got a non-deterministic way of doing it, and then I've got a deterministic way of doing it. Okay. In fact, the two languages are equivalent. Anything I can do with an NFSA, I could actually do with a deterministic one. Okay? I can build a deterministic one. I can build a deterministic finite state automata that corresponds to that non-deterministic finite state automata. And indeed, there's an algorithm to use it. Do it. You can find it online. Okay, there's a nice algorithm that will convert, that will take one of these automata here with all of its states and all of its arrows and convert it to something of that form. How do we feel about this 1 to 5? For every deterministic, there's a corresponding non-deterministic. I'm not going to prove it. I'm just going to do some examples. The proof involves an algorithm that's very long and nobody cares. I don't know why the polling is not. Did the robot hang? Hold on. Let's see if I think oh, there it was. Then it went. Sorry about that. Just as it figured it out, I deleted it. The bot hung. Okay. But as I said, the NFSA is simpler. Now, let's go into this thing. Now, this is saying 2 A's or 2 B's in the string in a row. Okay? Okay. Answer your question. Is there an algorithm for converting FSA and regular expressions for vice versa? Yeah, that's how Klein's theorem works. Klein's theorem works. If you want to actually read what Klein's theorem says, that's what it says. It's an algorithm for building the things. All right. Well, how do I do this? Two A's or two B's in the middle of a word. All right, so the first thing I notice is I've got this state here. This thing right here, this two A's or two B bits. Notice I've got no terminal and I've got no, terminating point and no initial point. So that's the exact same thing as saying this. Okay, that's the exact same thing. I don't care where it happens. Okay. All right. Now, if I want to do this with a non-deterministic formula, it's going to have trouble. But look how easy this thing is to produce with a deterministic finite state automata, non-deterministic finite state automata. I'm going to have a concluding state here with an anything. Now I'm going to have a B and a B. And then I'm going to have a concluding state here. And then anything. I'm going to have an A. And I'm going to have an A. And then I'm going to have a start. With an anything. Okay? How do we feel about that? 1 to 5. Will this match my regular expression? Now, I can do something really clever right here. Now, does that match my regular expression? This is one machine. All right? Anything with two B's will match. And anything with two A's will match. Kind of slick, huh? Okay. In other words, a non-deterministic finite state of automata is a beautiful way to deal with OR statements. Right? This is beautiful, right? It's got to match one of these two. How do you feel about that? 1 to 5. What's more, going back to the question above that I can't mention, there's an algorithm for converting regular expressions to non-deterministic finite state automata. Okay. Well, so there's a question: do I need a junk state in this problem? Remember, junk states are optional to begin with. I'm just throwing them in there because, but they're usually for a non-deterministic automata. You don't write it in there. You actually don't technically need to write it even for a deterministic finite state automata because you just start throwing out bad stuff. Because the junk always does basically the same thing. The only time I really care about a junk state is when I'm doing complements. Because when I'm doing complements, I want to accept junk. Because it's not no longer junk. It's, it's one man's trash, but it's the complement's treasure. Doing complements to these things, by the way, is a real pain in the neck. Do I need an arrow? Yeah, I should. You're right. Correction. I do need the arrow at the beginning. All right. Now, to answer that question, what I was doing before, there's an easy algorithm to convert regular expressions to non-deterministic finite state automata. And then there's an algorithm to convert non-deterministic state of finite state automata to deterministic state of finite state automata. And that's actually how Klein's theorem works. The version in the book is long and even more boring than the regular version. Klein's theorem, how part of Klein's theorem works. Klein, I guess, is his name. Okay. There's an algorithm to convert NFSA. There's an algorithm to convert regex to NFSA. There is an algorithm to convert NFSA to DFSA. Okay. That's basically how it works. All right, are there any questions about this? Okay. So everyone feels comfortable with this idea that I could give them a non-deterministic finite state automata and a bunch of expressions, and you tell me if they match. Okay. Okay, so that's a good test question. All right. Let's talk about NP. There are these things called Turing machines, and you will see Turing machines again. Okay? Now, we call an algorithm NP is in P if, oh, by the way, I do need to mention one other thing about these. All DFSAs are also in FSAs. Okay, so there's a hierarchy here. All right. So a deterministic finite state automata is a non-deterministic one. Okay. All right. Now, how much time do I have left? I have 5 minutes. I'm not going to get through it. P equals NP. All right. So we call a problem a problem in P if it can be solved by a deterministic Turing machine in polynomial time. Okay. We call a problem or just P. We sometimes just say P. If it can be solved by a non-deterministic Turing machine, in polynomial time. Yes, this is polynomial time. That is the $1 million question. No, really, it's the $1 million question. All right. And that's where we'll stop on this thing. Okay. If you want to read about this, the Wikipedia article is actually pretty good. The question that you have to understand is the thing you really need to understand is what is meant by a non-deterministic machine. Okay? So we have this hierarchy of complexity classes. Okay? And we actually don't know where the inclusions are. We know that this level at the bottom does not equal this level at the top, but we have no idea which ones are not equal. We think that P is a strict subset of NP, but we don't know. We do have, and we also think that P is a strict subset of P space, but we don't know. All right. And that's the big $1 million question. We don't know. If you want to read about complexity classes, you can get obsessed with this stuff. Go ahead. It's kind of obsessive stuff. It's really weird that we don't have a proof for this, that we don't know. we do know that diagonalization, we do know that NP space and polynomial space are equivalent. Okay. So the amount of memory that each would have to have is, I mean, the amount of memory is not equal, but it's polynomial. So things tend to grow, like Moore's law or exponential laws. Okay. So we know that computers get more and more efficient exponentially. And so anything that you can solve in polynomial time is going to be solvable at some point in the future. And we call these problems easy. Now, those polynomials can be really, really big. But the idea is that computers get faster and faster exponentially. Therefore, at some point, we'll be able to solve it. Whereas anything that's exponential time in origin, you can just keep adding more things to the problem. And it was... you can just add more time to the problem. Yeah, P space is equal to NP space. Okay, are there any questions about that? Well, it's a place to leave it. If I had another lecture, I'd do it. But this is a good place to end. We've just kind of talked about kind of the big open problem, the elephant in the room. Okay. A few announcements. It's been great teaching you all this semester. I wish we could have done more code. I wish we could have done some of the other things. It's unfortunate that this virus thing happened, but you know, we had some fun. I had some fun doing the Twitch thing. The new skill for me. I hope you all had fun with all of this. If you had a good time, you liked it, please go on Rate My Professor. Give me a rating. My name was Scott Grizzard. If you didn't have a good time, I'm sorry to hear that. Please go on Rate My Professor and give me a rating. My name was Savchuk. Dmitry Savchuk. Okay? Any questions, comments, issues, suggestions? Okay. Yes, I should consider a bonus lecture. The problem is that, you know, you get to watch it. I have to make it, and I still have to write your test for Wednesday and do a whole bunch of other stuff for calculus. So, yeah, that's all fun. All right, so that's the end of the class. I will be around. Oh, special extended office hours tomorrow. I will post those hours. You've been great, and I will see you all. Don't be strangers. Come on by when we get back on campus. Come take calc with me, or pre-calc. I'm teaching 2 sections of that next semester. 1 section of calc, if you're interested. And I will see you guys later. Again, office hours will be extended tomorrow. I'll post. Bye-bye.